getting 4 or 5 mails every evening from the students, you people who are watching my classes. They are asking me, is there any short method, any trick for the long questions? My dear friends, mathematics is not tricky. Okay. So if I give a double integral like this for a function that comes to my mind, you have to evaluate. There is no shortcut for that. If you want to prepare rice, you have to wait till the cooker is boiled, the rice is boiled. You cannot make any trick just like this and do the problem. You have to practice more and more to know how easily we can implement a method. But you cannot have tricks for these problems, particularly for multiple integrals, partial differentiation and vector calculus. You don't have any tricks for that. But that every day I am getting mails like that. But I want to tell you very clearly, even as a professor from either me or a professor from IIT or Massachusetts or Stanford, anything else for that matter, even from the heavens, cannot tell you any tricks to solve the problems. If you want to crack these problems, you have to do. That is the only trick we have. Okay? With that one small statement, just I want to go further. Just once recapping the definition of Green's theorem in a plane. So it's a relation between line integral and double integral in a plane. Mind you, Green's theorem is defined only for a two-dimensional regions, that is in a plane. If R is a closed region in xy plane bounded by a surface bounded by a closed curve C, and if m of xy and n of xy are continuous functions having continuous first order partial derivative, that means mxy and nxy are to be continuous, and dou m by dou x, dou m by dou y, these things. Similarly, dou n by dou x and dou m by dou y must be continuous. Then line integral over C, m dx plus n dy is equal to double integral over R, dou n by dou x minus dou m by dou y. This is called Green's theorem, and we have seen some problems also on this the other day. Now comes Stokes' theorem. See, I said Green's theorem is a theorem defined only in a two-dimensional plane regions, whereas Stokes' theorem and the next theorem, that is Gauss divergence theorem, these two theorems are defined in a space. Okay, regions in a space. It is a relation between surface and line integral. Just like Green's theorem, only difference is Green's theorem is defined over a plane and Stokes' theorem is defined on a space, that means three-dimensional regions. Let f bar be a vector function having continuous partial derivatives in a region in space containing open two-sided surface. I think we have defined this open surface as two-sided surface earlier. Okay, bounded by a simple closed curve C, then double integral over S del cross F n ds is equal to integral over C f dot dr, where ds is small area element on the surface S and n cap is the outward normal to that small element ds, area element ds. That means if this is a surface, just take a small element on this surface called ds. Okay, this element. So if the outward drawn to this at the small element is n bar, then n bar into ds is the area element, that is n bar ds, that is called vector area. It's a small area element with the direction normal to the surface, that is called vector area, and curl f dot nds is equal to integral over C f dot dr. If f is equal to fni plus f2j plus f3k, and if f3 is equal to 0, that means what we are doing, the component along z axis, if it is 0, that means f1 plus f2i, then Stokes' theorem reduces to Green's theorem. So it is to say that Stokes' theorem is an extension of Green's theorem, or Green's theorem is a particular case of Stokes' theorem when the third axis, that third dimension is neglected. So this is also clear, important point to make note of it. So let us see few problems on this surface integral. Prove that line integral over C f grade f dot dr bar is equal to 0. By Stokes theorem, f grade f dot dr bar. See, what happens is when we apply these theorems, the equations become very simple. That's why only trick is practice. If you know how to apply Stokes theorem effectively, then it can be solved in 1 or 2 steps. If you don't know how to apply Stokes theorem, you are not good at that, then you have to take long time. So if you apply this line integral, Stokes theorem to line integral, f dot dr, this is, let us say, this is the capital F bar. Dr is equal to, what is that? Del cross F. So curl of f grade f dot nds. So f curl f, if these properties we have done, del cross f g bar is equal to grade f cross g bar plus f times curl g bar. If you apply this property, then curl of divergent gradient is 0, and then cross product of the same vector a cross a is 0. So simply this integral becomes 0. So integral C f grade f dot dr is equal to 0 because we have applied Stokes theorem. If you don't know how to apply Stokes theorem, it takes a very long time. Do that, f grade g dot dr is equal to so on and so forth. By Stokes theorem, f grade g dot dr is equal to curl f dot ns. This is our f now. So curl of f grade g dot nds, because f grade g is a function now. So curl of that we are considering del cross f del g dot nds. So again, if you apply this cross product on this, it becomes grade f plus grade g plus f curl grade g. So this becomes curl grade f cross grade g dot nds. So this becomes again 0. Evaluate integral C f dot dr, where f is equal to 2y square I plus dx square j minus 2x plus z into k, and C is the boundary of the triangle with the vertices 0, 0, 2, 0, 0 and 2, 2, 0. Okay, easy if Stokes theorem is applied. So f dot dr becomes surface integral curl f dot nds. So for this f, first I am finding out the curl, that is I, j, k, dou by dou x, dou by dou y, dou by dou z, 2y square 3x square minus of 2x plus z. This is how we find the curl of a vector point function. So if you solve this, this becomes, if you simplify this, you will get 2j plus 6x minus 4y times k. So if you observe the points here, 0, 0, 0, z component is 0, 2, 0, 0, z component is 0, here also z. That means the points are considered in xy plane. So in this, that means when you neglect z, the points are 0, 0, 2, 0 and 2, 2. It's a triangular region like this. Okay. So line integral f dot dr becomes surface integral curl f is 2j plus 6x minus 4y into k, okay, dot n. Because this now this region is considered in xy plane. What is n bar? To xy plane. This is xy plane. K bar means along z axis. So n bar becomes outward normal. Normal to this given region is along z axis, that is k bar. So curl f dot n becomes 2j plus 6x minus 4y k dot k. So that means 6x minus 4y we get here dx dy. But now in this xy plane, this is a triangular region. So we have to write the limits of y and x now. So if you go along, as we discussed in multiple integrals, to find the limits of y, if you try to go along any line parallel to y axis, the region starts with like this. When you go like this, either here, here or here, when you go like this, you enter the region through x axis. The x axis means that is y is 0. And once you start entering the region, go ahead, but when do you leave the region? When you leave the region, you will be passing through the straight line y is equal to x. That means you enter like this, go ahead, then this is the exit here. Exit is through the line. Any point on the line y is equal to x. So the limits of y is x-axis, that is y is 0, and straight line y is equal to x. So limits of y 0 to x. Like that, straight line like this. The line goes like this to infinity, but we are not considering till infinity. Up to we are considering x from 0 to 2. So they are the limits of x. So 0 to 2, 0 to x, 6x minus 4y dy dx. That comes out to be 32 by 3. So we simply are applying the line integral. If you don't apply line surface area Stokes theorem, what you have to do? First we have to find the integral like this, then like this, then add. You have to do integration 3 times. Evaluate into lower c x plus y dx plus 2x minus z dy plus y plus z dz, where c is the boundary of a triangle with vertices 0, 0, 0, 1, 0, 0, 1, 1, 0. F dot dr is x plus y dx, 2x minus z dy plus y plus z dz. We know that f dot dr is, if f is f1i plus f2j plus f3k, and dr bar is I dx plus j dy plus z k dz, then f dot dr is f1 dx, f2 dy, f3 dz. So when the function integrand is given like this, you have to identify the function. f1 dx we have, that means f1i, f2 dy means f becomes j component of f becomes 2x minus z, here y plus z into dz becomes the component of f along z axis y plus zk. So f is x plus yi, 2x minus zj plus y plus zk. So to apply Stokes theorem, you need curl f. So ijk, dou by dou x, dou by dou z, x plus y, 2x minus z, y plus z. You simplify this, 2y plus k. Once again, if you see the points now, when you apply this curl f, line integral c f dot dr is equal to surface integral curl f dot ds. Curl f is now known to you. But where is the region now? 0, 0, 0, 1, 0, 0, 1, 1, 0. Again, z is 0 for all the points. That means the points are given in xy plane. That means it's a triangular region again in xy plane like this. So, when you are in xy plane, n bar becomes, that means normal to xy plane means along z axis unit vector is k bar. So, curl f bar dot n bar is k. So, curl f is 2y plus k dot k is 1. So curl f dot nbx becomes 1, ds becomes dx dy. You need not find the limits of integration here, just like in the previous problem. Why? Because here we don't have a function. It is simply double integral dx dy. If you see the previous problem, we have 6x minus 4y. We have to integrate this function. But here f is 1. When f is 1, what does the double integral dx dy represent? We discussed in multiple integrals. That represents the area of the region. That means here it is a area of triangular region. So it is same as the area of this right angle triangle, that is half BH. Half in base is, this is 1, 0, 1, 1, 0. So base is 1, height is 1. So integral over c f of dr becomes 1 by 2. Okay. Use Stokes theorem to evaluate curl f, double integral over s curl f dot ds over the surface of the paraboloid. So here what happens? If you don't apply this line integral, you have to apply. Okay. Let us see how the problem is done. Z plus x square plus y square is equal to 1. Z greater than or equal to 0. F is equal to y plus z, zj plus xk. Curl f dot nds is equal to line integral f dot dr. F is given to you. So yi plus zj plus xk dot dr is idx plus jdy plus kdz. So this is y dx plus z dy plus x dz. Okay, the line integral over c of y dx. Okay. So the parametric, because this equation is x square plus y square is equal to 1. x square plus y square, I think there is a mistake here, z is not there. This curve is only x square plus y square is equal to 1 and z greater than 0. So that means x square plus y square is equal to 1 means we are in xy plane. So z becomes 0. That's why we use this z is equal to this z plus a spelling mistake. We have z is equal to 0 and dz is equal to 0. Then this becomes simply y dx. And we are in xy plane, circle. So the curve is a circle. So x is equal to cos theta, y is equal to cos sin theta, because the radius is 1 unit here. I have taken r is equal to 1 here. X is equal to r cos theta, y is equal to r sin theta actually, because r is equal to 1, x is cos theta, y sin theta. So dx is minus sin theta d theta. So curl f dot ds becomes f dot is y is sin theta and to dx is minus sin theta d theta between 0 to 2 pi. This answer is minus pi. And the last thing, the theorem that we have is Gauss divergence theorem. Till now we have considered the relations between surface integrals and the line integrals. And Gauss divergence means is a relation between surface integrals and volume integrals in a space, that means three-dimensional regions. Let f be a vector function having continuous partial derivatives in a volume V bounded by a closed surface S, then double integral or S f dot n ds is equal to volume integral div f dx dy dz. So it is a relation between surface and volume integral. Surface integral of f dot n ds is equal to volume integral of div f dx dy dz. Let us see how we can apply these problems. Evaluate surface integral axi plus byj plus ezk. Mind you, just here it is given as integral, single integral only, but over S and SE surface. Even if you write like this when and mention that SE surface, we have to treat this as a double integral. Don't assume that it is a line integral, single integral. So surface integral axi plus byj plus ezk dot nds, where S is the surface of the sphere, x square plus y square plus z square is equal to 1. So this is f dot in ds. So f is axi plus byj plus czk. So if you want to apply Gauss divergence theorem, what is required? Divergence of f del dot f. So what is div f? Dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. That is dou f1 is this one, by dou x is a, dou f2 by dou y is b, dou f3 by dou z is c. So a plus b plus c. So surface integral f dot n ds is equal to div f dv. That means triple integral over v. Div f is a plus b plus c is a constant dv. So here, just like in double integrals, when the function is equal to 1, double integral dx dy represents area. In triple integrals, when f is 1 and triple integral of dv becomes the volume of the given surface, volume of the region bounded by the given surface. So this is a plus b plus c into v. But what is the volume of the sphere? 4 by 3 pi r cube. So for this sphere, so this is the volume of any sphere, v is equal to 4 by 3 pi r cube. But for a given problem, what is radius? Is 1. So this becomes v is equal to 4 by 3 pi. So if you put it here, the surface integral f dot n ds is equal to a plus b plus c into v, that is 4 pi by 3. So using these theorems, you can solve the problems easily. Evaluate surface integral f dot n ds if f is equal to so and so, we have the cube x is equal to 0, x is equal to a. So cube is given now, three-dimensional region, cube. So this you want to evaluate using Gauss divergence theorem. F is given to you, f square x square I plus y square z plus z square k. So to apply Gauss divergence theorem, you need to find divergence of f. So dou f1 by dou x, that is x square, dou f2 by dou y plus dou f3 by dou z. Dou by dou x x square, dou by dou y of y square, dou by dou z z square, then becomes 2 into x plus y plus z. So the surface integral by Gauss divergence theorem becomes div f dv. So that means 2 into x plus y plus z dx dy dz. So for a given cube, all the straight lines, all the sides are given with planes. So the limits of A, B, C, x from 0 to A, y from 0 to B, z from 0 to C. If you use the limits here, then the answer is, evaluate this, becomes A plus B plus C into ABC. And that is the surface integral. Evaluate f dot and ds f is equal to xyi plus z square j plus 2yzk over the tetrahedron bounded by x is equal to 0, y is equal to 0, z is equal to 0, and the plane x plus y plus z is equal to 1. We have considered regions like this x, y, z, like this x axis, y axis, z axis, and tetrahedron means if you take x plus y plus z is equal to 1 with equal intercepts on x axis, y axis, z axis. So it's an inclined plane like this. This is the region. So this is your region. In this region, you have to find the triple integral. So f is given. Div f is dou f by dou x. That means y. Dou f2 by dou y. There is no y term here, so it becomes 0. Dou f3 by dou z is 2y. So y plus 2y is 3y. So f dot and ds is div f is 3y dx dy, because this is the region now. Z changes from, this is z axis. So this is z axis. Z change from 0 to the plane. Like this, z starts here from 0 on this plane, goes up to the plane x plus y plus z is equal to 1. What is z on this plane? Z is equal to 1 minus x minus y. So if you integrate, just put dx, dy, dz, because the limits are in terms of x and y, the first integration should be with respect to z. So integral of dz is z. If you put the limit 0 to 1 minus x minus y, becomes y into 1 minus x minus y dx dy. Next integration should be with respect to x and y, because the limits of one integral are given in terms of x. That means there must be the limits of y. So we have to integrate with respect to y first. So then y square by 2 minus xy square by 2 minus y cube by 3 between 0 to 1 minus x. This is what we get. Then integrate with respect to x, we get, and put the limits, we get 1 by 8. So these are some problems, and some of the problems in the problems I have given in GATE question papers are taken from the GATE forum material, because it is very difficult to collect the problems at different sources. And I was searching, I got a material from GATE, and I have taken the screenshots of those material, so to give you the idea of the GATE question. So this is my sincere acknowledgements and thanks to GATE for material. So this is about vector calculus, and let us see. I have prepared some, not many, I have 20-25 multiple answer questions, multiple choice questions on vector calculus. Very small problems. You can just go through them once. Phi is scalar point function, then grade phi, gradient is always a vector. A vector f is said to be solenoidal. You know the answer. After going through this lecture, there must be a portion to answer what is a solenoidal function. If A is a constant vector, R is equal to xi plus yz plus zk by j, this is yz plus zk, then divergent of A cross R you can find out. Take A is equal to A1i plus A2j plus A3k. Here A1, A2, A3 are constants. Xi, yj, zk. Then find A cross R, then divergence of A cross R, do it. F is equal to x plus 3 by I, y minus zj, as x plus 3zk is solenoidal, then what is value of P? Solenoidal, you know what is solenoidal. So if you apply the principle, you will get the value of P. The curl function, for a vector function, what is curl of curl f? Curl of curl f means, so then you can identify the identities I have given to the given you the identities. From that you can find out these answers. Curl f is equal to 0, then the vector f is called solenoidal, irrotational, constant, potential. You know what is the answer. Find the value of P such that f is irrotational. Irrotational means del cross f must be 0. Find del cross f equal to 0, get P. Del of log R. This problem I have given in the workout problems. I have given the problem log R, the presentation. Directional derivative of xy plus yz. You have done good number of problems on this. Grade f. This is, let us say this is f. Grade f dot unit vector, the direction. So f is x square I plus y square j plus z square. Then curl f is equal to, you have to find curl f. Work done by force in moving a particle on the straight line joining these 2 points. You know what is f dot dr, line integral f dot dr gives you the work done. So divergence of this vector, you can find it dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So that becomes 2x, this becomes 0 minus 3z square. Direct question. F is x plus y into I, y minus z into j. Then f dot dr along y square is equal to x between 1, 1, 2, 4. Line integral we have done. I think this problem also. F is equal to I plus 2zk. Then find phi such that f is equal to grade phi. I have told you to differentiating with respect to x, integrating with respect to x with respect to y the problems. That's problems of that type. The unit normal to the surface. So find grade for this. Put this point, then take the unit normal, divide by magnitude. Reduction of surface of S on xy plane. This is when S is a surface in the space, when you consider the projection while doing surface integrals, we have discussed S1, S2, S3. If S1 is the projection in xy plane, then ds becomes dx dy by n dot k. By Green's theorem, below C 2x by dx plus 3x by c. You say that big problems, tricks, very lengthy problems. So see here, Green's theorem application, direct problem on Green's theorem. You have to do the problem. There is not no way. There is no way out. You want to do it, you have to do it. That's all. The vector integral theorem connects the line and surface integral is Green's, Gauss, Stokes, or divergence theorem. Vector integral theorem connecting line integral and surface integral. In fact, Green's theorem also connects. Stokes theorem also connects. This is in plane, is a 3-dimensional geometry. Both answers are correct. It should be given as in a plane, something like that. The theorem which gives relation between surface and volume integral is obviously Gauss divergence theorem. Phi is given, del dot del phi, can calculate this easily. So some problems for practice. So with this, we have finished vector calculus, and next topic that I want to discuss is, see, all these topics I am taking in during these 10 or 12 days is common topics almost all for all the branches except CSE and IT. CSE and IT, they have very little bit of mathematics. So for all other branches, we are dealing with only the common topics that we have in common to all the branches. Okay. So the next topic that we will be dealing is linear algebra. Okay. So linear algebra deals with, basically at our graduation level, linear algebra means it is some theory related to matrices and its properties. But linear algebra in a broader sense, a lot of meaning it comes. We have to deal with vector spaces, linear transformations, so many things. Inner product spaces, so many things we discuss in linear algebra. But at our graduate level, undergraduate level, BTech level, and we have only the basics of linear algebra like matrix theory. Let us see. So before going to the details of this thing, first let me give a brief introduction to matrices also, because you have done these matrices way back. Maybe your BTech first and second years. Maybe some other reason also, the diploma candidates who completed their BTech and they after diploma and they join in second year. What we call lateral entry students. Okay. For the lateral entry students, they don't do this matrices theory and all that. So let us go through the basics of matrices. I know you are very much familiar, most of you, but still just be patient. A matrix is a rectangular array of m into n numbers arranged in m rows and n columns. Numbers means here they can be functions also. These numbers are the elements known as elements or entries are enclosed in a bracket. This structure is called matrix structure. So the number of rows, it is a matrix is denoted by the order of the matrix is denoted by m into n, where m is number of rows and n is number of columns. If you see how many number of rows we have, this is one row, this is second row. So we have two rows and how many columns? 1, 2, 3, 4, 4 columns. So the matrix is called 2 by 4 matrix. Here it is how many rows? 1, 2, 3. How many columns? 2. So 3 by 2 matrix. If number of rows and number of columns is same, then it is called a square matrix. So 2 by 2 matrix, 3 by 3 matrix. So each row is if a matrix contains only one row, then it is called a row matrix. If it has only column, then it's called column matrix. Then a square matrix in which all the elements except those along diagonal are 0. That means along diagonal only we have elements, all others are zeros. Then such a matrix is called diagonal matrix. And if A and B are two square matrices and K is any scalar, then trace of a matrix. What is the trace of a matrix? We again will come back to this point, trace in eigenvalues and eigenvectors. Trace means sum of the diagonal elements in a matrix. Sum of the diagonal elements in a matrix is called trace of the matrix. Simply, if I ask you to find the trace of this matrix A, you add all the diagonal elements. What is that? 3 plus minus 1 plus 6 plus 2. That means 6 plus 2 8 minus 1 7 plus 3. The trace of the matrix is 10. Okay. So this one, an improvement of this. Here all the diagonal elements are non-zero. If all of them are constant, the same value. This is also diagonal matrix, but here the elements may be different. Here they are not different. In such case, it is called a scalar matrix. And then comes unit matrix or identity matrix. So if all the diagonal elements are ones, 1 0 0 0 1 0 0 0 1, then it is called a unit matrix or identity matrix. Then comes nilpotent matrix. A square matrix A is said to be nilpotent if A power m is equal to a 0 matrix, where m is a positive integer. Then A power m is equal to 0, then the A is called nilpotent matrix, and m is the least positive integer such that A power m is equal to 0, then m is called the index of the nilpotent matrix. M is called the index of the nilpotent matrix. You may have straight away you can ask, say for example, for a given matrix 3 by 3 matrix A cube is equal to 0. What is the index of the matrix? Is 2 3 1 0. The question may be like this. So for a given 3 by 3 matrix A cube is equal to 0. Okay. Then index of the matrix is alternatives A, B, C, D. That means A power m is equal to 0. And so the index becomes 3. Idempotent matrix. A square matrix A is said to be idempotent if A square is equal to A. If A square becomes equal to A, then it is called idempotent matrix. If this A square is equal to I, if A square is equal to, then we call involutory matrix. Involutory matrix. Okay. Then comes transpose of a matrix. If you interchange the rows and columns of a matrix, then it is called the transpose of a matrix. That means if you 2, 4, 5, 6, 7, minus 7, 2, 9, 3, 8, that means A transpose becomes change the rows into columns and columns into rows. So 2, 4, 5, the first row becomes first column, 6 minus 2 becomes second column, 9, 3, 8 becomes third column. So A transpose is 2, 6, 9, 4, minus 7, 3, 5, 2, 8. Properties of transpose. If A transpose and B transpose are the transpose of A and B respectively, then A transpose whole transpose is A. A plus B whole transpose is A transpose plus B transpose. Constant times A whole transpose is constant has no transpose. Real number, even if you transpose, you will get the same thing because you order one by one, it will be the same thing. Becomes K into A transpose, K is any scalar. AB whole transpose becomes B transpose A transpose. This is an important point. Then symmetric matrix. A matrix is A said to be symmetric if A and A transpose are same. You transpose the matrix, then again if you get A, then it is called a symmetric matrix. That means 1, 2, 3, 1, 2. Symmetric means the rows and columns are symmetric. The first row and first columns are same. The second row and second columns are same. The third column and third row are same. So then it is called a symmetric matrix. Then skew symmetric matrix. A square matrix is said to be skew symmetric if A transpose is equal to minus A. A transpose is equal to A, it is symmetric. A transpose is equal to minus A, then it is called skew symmetric. If you see this is 3, this is minus 3. Minus 5, 5, 8, minus 8. What happens if you have non-zero elements along this? They fail this condition. So for anti-symmetric matrix, for a skew symmetric matrix, the diagonal elements are always must be 0. Then orthogonal matrix. A square matrix is said to be orthogonal if A transpose is equal to A inverse, or else A into A transpose is equal to A transpose into A is equal to I. Then we say that it is diagonal orthogonal matrix, or else A transpose is equal to A inverse. Then A is said to be orthogonal matrix. Properties of orthogonal matrix. The inverse of an orthogonal matrix is orthogonal and its transpose is also orthogonal. Clearly, A is an orthogonal matrix. So A inverse is equal to A transpose. Because A is orthogonal, A transpose is also orthogonal, then A inverse also becomes orthogonal. If A is orthogonal, determinant of A is equal to plus or minus 1. If A and B are orthogonal matrix, each of order n, then A and B into A are also orthogonal matrices. These questions, these points may be directly asked as questions. Maybe a square matrix A is said to be orthogonal if A transpose is equal to A transpose is equal to minus A. Third option, A transpose is equal to A inverse. A into A transpose is equal to I. Maybe A, B, C, D, not 4 questions, 4 options may be given for this point. Then another bit, if A is an orthogonal matrix, the determinant of A is equal to plus or minus 1, B plus or minus 0, C less than 0, D we cannot say. 4 options, it can be a question, direct questions, multiple choice questions. Then A and B are orthogonal matrix, each of order n. Then one of the following statements is true. Identify it. AB is only orthogonal. 2. BA is also orthogonal. C. AB and BA are orthogonal matrix. D. The AB and BA are not orthogonal matrix. 4 options. So from these theoretical points also, in matrix theory particularly, we are getting multiple choice questions. So don't throw away because there are simple theory questions. You are getting direct questions from these theory aspects. I will show you some gate questions later. You will see some of the basic theoretical ideas they are asking as questions in multiple choice questions. So determinant of a matrix. If it is a 2 by 2 matrix, the determinant is defined by AD minus BC. If it is A, B, C, D, then determinant is denoted by like straight lines besides the matrix elements A, B, C, D. So AD minus BC is called determinant of a 2 by 2 matrix. So 2, 3, 5, 7. AD, BC minus 1, 2 7s are 14 minus 15 minus 1. Minor of element in a square matrix, the minor of element AI is determinant of the matrix obtained by deleting jth ith row and jth column of the element. So, if you want to find the minor of 1, that means you neglect the row and column to which the element belongs. That means this row and this column. The remaining elements 5, 9, 11, 6. The determinant of that is called minor of 1. Say for example, you want to find the minor of 11. Neglect the row and column, that means this row and this column. Remaining elements are 1, 3, minus 4, 9. Determinant of that 9 plus 12. That's how we get the minus. Then the cofactor. So, in the matrix, while finding these cofactors, each element is given a sign. Let us say, if I take the ith row jth element, jth column element, then the sign is minus 1 power I plus j. That means the first row, second column, if I want to take the first row, second column. Let us say this element I want to take. First row, so I is 1, second column j is equal to 0, j is equal to 2. So the sign is minus 1 power I plus j. So let A be in a square matrix. The minus of Aij is multiplied by minus 1 power I plus j is called the cofactor. Determinant of the matrix. The determinant of a square matrix is defined as sum of the product of the elements of any row or column with the corresponding cofactors. So you can find the determinant of a matrix about any row or any column in the matrix, either this row, this row, this row, this column, this column, this column. Whatever row or column you consider, in that row or column, the sum of the product of the elements with these cofactors. That means, if for example, I take the first row, 1 into cofactor of 1, this one, 20 plus 6. And the sign of this is minus 1 power 1 plus 1. This is first row, second column, I is 1, j is 2, so minus 1 cube. Neglect these elements. 0, minus 3. Like this, we get a determinant. So vector concept we don't need that much. So I'll start with, I don't want to bother with unnecessary ideas of vector spaces which are not there, most of you. So leave with linear dependence of vectors. This linear dependence vectors, independent vectors is very, very important for us. In linear algebra. Just I think, just hold on a moment please, I will open another file for this. Yeah. Okay. Finished of this thing. I have included some more new points in this. That's why I am using a new presentation here. Yes. So determinant of this example is so and so. So determinant of 1 into cofactor and this mind of this, like this we get properties of determinants. Because these properties are missing in the previous presentation. That's why this is a modified version of the presentation. That's why I am opening this presentation. Properties of determinants. If each element of a row or column of a square matrix is 0, then determinant becomes 0. If one row is completely 0, if one column is completely 0, then determinant is 0. If two rows or columns are interchanged, then the sign changes. Say two rows are changed, that means there will be change of sign in the determinant. But if it is 0, it will be 0. If each element of a row or column of a square matrix is multiplied by a constant, then each element of a row, not each row. Say for example, second row if you take and multiply each element of second row with a constant 2, then the determinant of the matrix resulting is k times the actual determinant. If you take matrix A and find determinant of A, let us say D1. And in the matrix A, take the second row, multiply with 2. Okay. The resulting matrix, let us say, call B. Then determinant of B is equal to twice determinant of A. If A is an n by n matrix, then Ka is equal to K power n into determinant A. Like that, if you multiply every element of matrix with a constant K, then this will be k power n into determinant of A. The corresponding elements of two rows or columns are in the same ratio, then determinant is 0. Scalar one row is or column is constant times the other row or column. That's what we mean. Then the determinant becomes 0. Determinant of A is same as determinant of A transpose. The next one is determinant of AB is equal to determinant of A into determinant of B. And then for any positive, this is a, I'm telling you these points may be directly asked as questions. I repeatedly am telling you some of the questions are like that in previous GATE papers. So all the properties that we discuss, you have to learn them thoroughly. So determinant of A into B is determinant of A into determinant of B. For any positive integer, determinant of A power n is equal to determinant of A power n. If A is a triangular upper or lower triangular matrix, then determinant of A is equal to product of the diagonal elements. Product of the diagonal elements. I think in last previous 2018 or 19 GATE paper, this question was asked as a with a matrix. A is given to you and then ask the eigenvalues. The determinant of the matrix. Linear dependence of vectors. A V of B vector space, a finite subset alpha 1 alpha 2 alpha n of vectors, let us say alpha 1 alpha 2 alpha n are vectors, they are said to be linearly dependent set if there exist scalars a1 a2 an, not all 0, such that a1 alpha 1 plus a2 alpha 2 plus so on so forth an alpha n is equal to 0, but all these constants need not be equal to, even if there exists at least one constant which is not equal to 0, then we say that these vectors are linearly dependent. Question now is, sir, we are dealing with matrices. Till now we are discussed the cofactors minus and determinants. Then why vectors suddenly? Again, see, another important notation in linear algebra is that the rows or columns of any matrix are considered as vectors. If you take a 3 by 3 matrix, the first row is called 3 by 1 matrix. The second row is also a vector. Third row is also a vector. The first column considers a vector. Second column can be considered a vector. Third column can also be considered as a vector. In that sense, you have to consider linear dependence vectors in no way related with. Of course, in a long shot we have some relation, but in no way related with your vectors like I bar, J bar, K bar. Okay. So any n array can be treated as a vector in linear algebra. In that sense, when I say linear dependence of vectors here in matrices theory, linearly independent rows in a matrix. The first row alpha 1 is the first row, alpha 2 is second row, and alpha 3 is third row. Then if you have a1 into our first row plus a2 into second row plus a3 into third row is equal to 0, and if at least one of them is non-zero, the constant is not equal to 0, then we say that the vectors are the rows are linearly dependent. If all ai's are 0, then the rows are linearly independent. Similarly with the columns. Then how to check the linear dependency? Okay. So consider these vectors as matrices. Find the determinant of the matrix. If it is 0, we say that the vectors are linearly independent. If it is not equal to 0, then we say that it is independent. Let us see one or two examples. Check whether the vectors 1, 3, 2, 1, minus 7, minus 8 is linearly dependent. One classical approach is we have to find a1, a2, a3. No. So here a, b, c arbitrary constant I have taken a into 1, 3, 2 plus b into 1 minus 7, 8 plus c into 2 minus 1. If whenever this is 0, it says that whenever this is 0, the constant, if all the constants are zeros without any alternative, then we say they are linearly independent. If at least one of the constants is not equal to 0, then we say that linearly dependent. Let us see if all are 0 or not. So what is the first quantity? Here a, here is b plus c. The right hand side the first component is 0. Second element is 3a minus 7b plus c the right it is 0. 2a minus 8b minus c is equal to 0. If you solve these equations, you get a is equal to 3, b is equal to 1, c is equal to 0. All the constants are not equal to 0, are different from 0. So, from the definition, if there exist scalars a1 not all 0, then they are linearly dependent. Otherwise, if you use this test, take the determinant of the vectors. So I write them as vectors, as rows 1, 3, 2, the first row, 1 minus 7 minus 8 second row, 2, 1 minus 1 third row. Find the determinant. If it is 0, then they are linearly dependent. If you are good at finding determinants, better convert the rows into a matrix, find determinant. If it is 0, linearly dependent. Check whether the vectors 1, 2, 0, 0, 3, 1, minus 1, 0. You can approach either way, this equation method or maybe determinant. So a into 1, 2, 0, b into 0, 3, 1, c into minus 1, 1 is equal to 0. So a plus 0, b minus c, a minus c is equal to 0, a is equal to c. Second element 2a plus 3b, c is equal to 0. Last row, b plus c is equal to 0. A is equal to c. So b becomes, because a is equal to c, b is equal to minus c. So if you solve them, a is equal to b is equal to c is equal to 0. So whenever all the constants are 0, they are linearly independent. That's how we get. Otherwise, find the determinant of 1, 2, 0, 0, 3, 1 and minus 1, 0, 1, just like this. Okay. If it is 0, then we say that dependent. If it is not equal to 0, we say that they are independent. Which are the following are linearly independent set of vectors in R3? 1, 0, 0, 1, 1, 0, 1, 1, 1. Here, like this is equal to 0, 0, 0. If you find the equation a plus b plus c is equal to 0, b plus c is equal to 0, c is equal to 0, solve a is equal to b is equal to 0. So they are linearly independent. So the second problem, a, b, 1, like this again, a minus b is equal to 0, a minus 2c is equal to 0. The last element is a plus b plus c is equal to 0. Because a minus b is 0, a is equal to b. A is equal to 2c. So b is equal to 2c. So a is equal to 2c, b is equal to 2c. So c becomes b by 2. The vectors are a plus b plus c is equal to 0, b plus b plus 1 by 2, b is equal to 0. So it must be, b must be 0. When b is 0, a is 0 and c is 0. So these vectors are linearly independent. So similar way you can do this problem. And exercise on this. Then basis of vector space. A subset S of vector space V of S is to be a basis of V if the elements of S are linearly independent and the linear any element of V can be expressed as a linear combination of S. So forget about these ideas, they are a bit away from our study. So we'll go straight to the rank of a matrix. Now most of you have done these problems on rank of matrix at BTech level. So there are two senses here to define the rank of a matrix, two methods to solve the problems to find the ranks of the matrix. One is using the zeroth nature of minors and the other one is using the concept of linearly independent rows in a matrix. Rather, linearly independent vectors in a matrix. So, what is the definition of rank of a matrix? Let A be a non-zero m by n matrix. The rank of a matrix A is the order of the largest non-zero minor of A. See, terms are very typical and tricky. Follow the terms. The rank of a matrix is the order of the largest non-zero minor. So if you take a 3 by 3 matrix, you will be having a 2 by 2 minors and the largest minor is 3 by 3. So that is determinant. The determinant is not equal to 0, then the order of that minor becomes the rank of the matrix. If determinant is 0, then we will have 2 by 2 minors. If there exists at least one 2 by 2 minor which is not equal to 0, then rank of A becomes 2. So that means the R is the rank of A if 1. Every R plus 1 minor of A is 0. Okay. And there is at least one rth order minor of A which is not equal to 0. Rank of A is denoted by row of A. Row. Properties. Rank of a matrix is always unique. A given matrix cannot have 2 or 3 ranks. It is always unique. Every matrix will have a rank. If all the elements are 0, then the rank of the matrix is 0. The rank of the unit matrix In is n. If A is a matrix of order m by n, then the rank of A is always less than or equal to minimum of m and n. And rank of A is equal to rank of A transpose. Then, to find the ranks of the matrix and to deal with the system of linear equations and other things, we need one more important concept called row column transformations. Row and column transformations. What are these row and column transformations? One is you can interchange any 2 rows or any 2 columns. Interchange any 2 rows or 2 columns. That is denoted by the transformation Rij if it is rows. If it is columns, if the columns are interchanged, ith column and jth column interchanged, then it is denoted by Cij. The multiplication of any row or column by a non-zero constant, that is denoted by K times Ri. This must be a non-zero constant. The third one is the addition of a constant multiple of the elements of any row or column to the corresponding elements of any row or column. You multiply any row or column with a constant, you add it to any other row, elements of any other row. That is the third transformation denoted by Ri plus Krj. Then one important form to find the rank of a matrix is echelon form. Echelon form. What is echelon form? The matrix is said to be echelon form if it satisfies the following 2 properties. 1. Number of 0 rows must be the bottom of the matrix. 0 rows, if any, must be below the non-zero rows. Non-zero rows. The number of zeros before the first non-zero element of a row is less than the number of zeros in the next row. If you see the matrix, understand a better way. So like this. If at all you have any 0 rows, it should be at the bottom of the matrix. And there should form a lower triangle matrix sort of thing with zeros like this. The number of zeros here is 4. Here if you see, the first non-zero element is 1. All zeros are before that. Here they are all non-zero elements. 0 is before that. Such a structure is called rank of a matrix. The advantage of echelon form of a matrix. When the matrix is reduced to echelon form using row transformations and column transformations, and finally the number of non-zero rows in the echelon form gives the rank of the matrix. A very important point to find the ranks of the matrix. Reduce the matrix to echelon form. That means something like this. Then the number of non-zero rows in the echelon form gives the rank of the matrix. So it is in the echelon form. As I said, the number of non-zero rows is the rank. So how many non-zero rows? 1, 2, 3. So the rank of A is 3 for this matrix. So find the rank of this matrix using transformations. 1, 2, minus 4, 5. 2, minus 1, 3, 6, 8, 1, 9, 7. For this clearly what we can say is rank of A is less than or equal to 3. Because we have 4 columns and 3 rows, and we have cited a property rank of A is less than minimum of number of rows and number of columns. So rank of A must be less than or equal to 3, the number of rows, and 4 number of columns. So if you apply R2 minus 2R1, R3 minus 8R1, then these two things must be 0. So the elements will change, it comes like this. Okay. Then R3 is equal to R3 minus 3R2. Multiply this with 3 and subtract, this will be 0. So this is what we get. Can we further reduce? No, you cannot further reduce to zeros any of the elements. So it is in the echelon form. It is in the echelon form. Maximum number of zeros from the beginning is at the lowest row. Okay. So once it is reduced to echelon form, the number of non-zero rows in the matrix is the rank of the matrix. How many? 1, 2, 3. So rank of matrix A is 3. So find the rank here using echelon form. This is the matrix we have. Observe, this is a skew symmetric matrix, whatever it is. So apply R1 and interchange R1, R2 like this. Then applying R3 minus 3R1, R4 minus 4R1, it comes like this. 1 minus 3 minus 1, 1 minus 3 minus 1, 1 minus 3 minus 1. Even these 3 rows can be reduced to zeros. So this is a matrix that we get. We cannot reduce any further. Okay, it's in echelon form. So number of non-zero rows is first and second. So rank of the matrix is 2. Another problem, A is equal to 1, 2, 3, 4, minus 2, minus 3, 1, 2. So if you apply the transformations and reduce this to echelon form, this is what we get. So rank of A is number of non-zero rows 1, 2. Others are 0 rows. So rank of A is 2. Exercise problems, the clear 4 problems, you can solve it. Then comes system of linear equations. The system of any equations in n unknowns in matrix form is represented by Ax is equal to B. We are dealing with linear equation. Linear equation means in n variables a11 x1 a plus a12 x2 so on and so forth a1n xn is equal to b1. See? That's a linear equation. Like that we have n equation in unknowns and then all system of equations can be expressed in the form Ax is equal to B, where A is called coefficient matrix and B is column vector and X represents solution which we want to find. Okay. If B is equal to 0, this is in general called a non-homogeneous system of equations. If B is not equal to 0. If B is equal to 0, this is called a homogeneous system. Ax is equal to 0 is said to be a homogeneous system. Otherwise, it is called non-homogeneous system. Then the solution of system of equations. Then how to find a solution of system of equation Ax is equal to 1. A system of equations 1 is said to be consistent. The system has a solution. If it has a solution, then we say that it is consistent. In matrix equation, it is always advised to discuss whether the system is consistent first before discussing the solution. First we have to check the consistency and then we find the solution. Because it takes lot of effort, you have to put lot of efforts to solve the equations. So instead of putting all the efforts, first you check whether the solution exists or not. That means check whether the system is consistent or not. If it is consistent, then you can find the solution. That is the idea. So a system is said to be consistent if it has a solution. And this one, then how many solutions can we have for this equation Ax is equal to B? One or many or no solution. What are the conditions we have? The given system is consistent, then it can have either unique solution or infinitely many solutions. You can have a unique solution or you can have infinitely many solutions for Ax is equal to B. A system of equation 1 is said to be inconsistent if it has no solution. If it has no solution, it is called inconsistent. Then what is the condition for consistency? How to check the consistency? How to check whether the solution is a system has a solution or not? So here the A is there and we consider another matrix here, what we call augmented matrix. Augmented matrix A augmented with B, we write like this. That means this B is written by the side of A as a column. That is called augmented matrix. So rank of A, it is equal to rank of A augmented with B, then we say that the system is consistent. If they are different, then the system is inconsistent, the system has no solution. Nature of solution. The system of equations Ax is equal to B is said to be consistent if rho of A is equal to rho of AB. Consistent and the solution is unique if the rank of A is equal to rank of A by B is equal to number of unknowns. The ranks are equal and if they are equal to the number of unknowns, then we have unique solution where R is rank and N is the number of unknowns. They are consistent, that means rho of A and rho of A by B are equal, and it has infinite number of solutions if the rank is less than number of unknowns. Rank of the system is less than number of unknowns, then we have infinite number of solutions. Inconsistent, as I said earlier, these two ranks are different from one another, then we say the system Ax is equal to B is inconsistent. Method of finding rank of A and A. So reduce the augmented matrix to echelon form. As I said earlier, to find the rank of the matrix, we reduce the matrix to echelon form. So here we are considering A augmented with B, what we call augmented matrix. Reduce this augmented matrix AB to echelon form by elementary row transformations. Mind you, to find the rank of the matrix, any problem, you can find row and column transformations. But when you want to apply this to system of equations, you cannot apply column transformations. Only row transformations only are allowed. Column transformations you cannot apply them. Put them in quotes. While solving this dealing system of equations, you should not use column transformations. Why we cannot use column transformations is, say for example, if I take this matrix, the quotient of x is 3, quotient of y is 1, quotient of z is minus 2. If I use column transformation, that means let us say if of x will be 1, y will be 3. That means the equation itself we are changing. You cannot do that. So while dealing with system of equations, column transformations are not at all entertained. They are not allowed. Only row transformations are allowed. Let us see how we check the consistency of system of equations using this idea. So check the consistent system of equation. X plus y plus z is equal to minus 3, 3x plus y minus 2z is equal to minus 2, 2x plus 4y plus 7z is equal to 7. So the matrix here is system is Ax is equal to B is like this. So we are writing the augmented matrix A B like this. So A will be written as it is 1 1 1 3 1 minus 2 2 4 7. Besides C, we write this B. This is A given A augmented B. Then reduce this matrix to echelon form by using row transformations. R2 minus 3R1, R3 minus 2R1, then these things will be 0. Further reduce it, this element, so we get like this. So if you close this last column, what is the matrix? The remaining matrix is echelon form of A. If you close the last, repeat it, please listen very carefully. If we close the last column, that is B, the last column corresponds to this vector. So if you close the last column, then the remaining part is 2 3 by 3 matrix is matrix A, the echelon form of A. So because it is the echelon form of A, what is the rank? Number of non-zeros. So rank of A is 2. But when you consider this column also, this is A by A given A by B. So this is also echelon form. How many non-zero rows? 3. So rank of this matrix is 3. So rank of A is 2. Rank of the augmented matrix is 3. They are not equal and the system is not consistent or the system has no solution. So 2x minus y plus 3z minus 9 is equal to 0. X plus y plus z is equal to 6. X minus y plus z is equal to 2. The given system can be matrix form x plus z like Ax is equal to B. Consider the augment structure 2 minus 1 3 1 1 1 1 minus 1 augmented with 9 6 2. Reduce this augmented matrix to echelon form. So it comes like this. So if you close the last column, this is the echelon form of matrix A. How many non-zero rows? 1 2 3. So rank of A is 3. So if you consider this column also, rank of A is 3. So they are equal and the given system is constant and we have a unique solution. Once it has a unique solution, you can find how to find it. We'll see how to find the solution. Like this. Okay, you have to give an okay, no problem. So if you once it is established that it is consistent, then you can go for the solution. Now go back from this echelon form matrix to the equations. What does the last row represent? What is the equation corresponding to the last row? Minus 2z is equal to minus 6. Minus 2z is equal to minus 6 or z is equal to 3. The last but one row is minus 3y plus z is equal to minus 3. So substitute z is equal to 3 here, get y is equal to 2. So the first row is x plus y plus z is equal to 6. So put y is equal to 2 and z is equal to 3 in this, we get x is equal to 1. That's how we get the solutions. X plus 2y plus 2z is equal to 2. 3x minus 2y minus z is equal to 5. 2x minus 5y plus 3z is equal to minus 4. Yeah. The last one is x plus 4y plus 6z is equal to 0. So put them in matrix form. So this is what we get. Ax is equal to B. Interestingly, we have 4 rows, 3 columns. It's a power determinant matrix. So consider the augmented matrix. That means matrix augmented with the constant. Yes. Last vector, column vector 2, 5, minus 4, 0. So by applying these so many transformations, we have what we get like this. Further using row transformations 1, 2, 2, 2, minus 8, minus 7, minus 1, 0, 0, 55, minus 55, 9, minus 9. So this is next we get. So this is finally, this is a echelon form of the augmented matrix. If you close the last column, what is the rank of A now? 2, 3 non-zero rows, rank of A is 3. So then if you consider the last column also, even then rank of the augmented matrix is also 3. Hence consistent. Hence the system is consistent. Now how to find the solution? The last equation says 0 into x, 0 into y plus 1 into z is equal to minus 1. So that is minus 1. Last but one row is minus 8y minus 7z is equal to minus 1. Okay. But z is equal to minus 1 if you put y is equal to 1. The first equation now x plus 2y plus 2z is equal to 2. So put x, y, z, whatever is known to you here. Z is equal to minus 1, y is equal to 1 in this. You will get y x also. So this is your solution. So under problem x plus y plus z is equal to 6, x minus y plus 2z is equal to 5, 3x plus y plus z is equal to 8, 3x minus 2y plus 3z is equal to 7. So the given matrix system is Ax is equal to B. So consider the augmented matrix 1 1 1, 1 minus 1 2, 3, 1, 1, 2, minus 2, 3, augmented with 6, 5, 8, 7. So applying some row transformations here, we are reducing the augmented matrix to echelon form. So what is the echelon form that we get? Like this. Once you close the last column, rank of A is clearly 3. Number of non-zero rows 1, 2, 3. And even if you consider the complete matrix, number of non-zero rows is 3. So rank of A is equal to rank of augmented matrix is equal to 3. So system is consistent. And then find the solutions. The last column, last row says minus 3z is equal to minus 9. So z is equal to 3. The second row says minus 2y plus z is equal to minus 1. So if you put z is equal to 3 here, y is equal to 2. So y is equal to z is equal to 3. Put them in the first equation, x plus y plus z is equal to 6. So x is equal to 6 minus this thing. If you solve this, we get x answer. Some problems as exercise. Solution of homogeneous equation. This is quite interesting. The homogeneous system of linear equations in matrix form is given by Ax is equal to 0. Ax is equal to 0. If rank of A is equal to R is equal to number of unknowns, rank of A is equal to R is equal to number of unknowns, then the given system Ax is equal to 0 possesses only a trivial solution. See, just by looking at the equation, what is the possible value of X? Let us say A is non-singular. That means determinant of A is not equal to 0. When determinant of A not equal to 0, you can find the inverse of A. So when you know A inverse, multiply both sides with A inverse, what happens? A inverse Ax is equal to A inverse 0 or X is equal to 0. So whenever A is invertible, that means determinant not equal to 0, X is 0. That is, X is equal to 0 is called a trivial solution. Now coming to the invertibility of A or determinant not equal to A. Determinant of A is not equal to A only when rank of A is equal to rank of R. That is, rank of A is equal to N. So there are all similar statements. Ax is equal to A is invertible, determinant A not equal to 0, or rank of A is equal to R is equal to N, the number of unknowns. Then the consequence is Ax is equal to 0 possesses only a trivial solution. So if R less than N, the given system Ax is equal to 0 possesses infinite number of solutions by assuming n minus r arbitrary constants to n minus r variables. How this n minus arbitrary constant will discuss. So if you observe these 2 points, the homogeneous system of equations, the solution is a trivial solution or you can have infinite number of solutions. So there is nothing like having a unique non-zero solution here. Never. You cannot say, you cannot ask whether the solution is unique. Not. It doesn't happen. Either it is a zero solution, that's what we call trivial solution, or it has infinitely many solutions. Let us see. Let's say consistency of x plus y is equal to 0, y plus z is equal to 0, z plus x is equal to 0. So this is the system of equations like this. The matrix A is so and so. So reducing the echelon form, it's like this. So rank of A is equal to 3, number of unknowns, the given system is trivial solution, that means x plus y plus z is equal to 0. So what we mean here, from this echelon form, if you write back the actual equations, what is the last equation? 0 into x plus 0 into y plus 2 into z is equal to 0. 2 into z is equal to 0 means z must be 0. The second equation is y plus z is equal to 0. Already z is equal to 0. Then what is y? 0. And if you put this yz in the first equation, x also becomes 0. So like that, whenever the rank of A is equal to rank of when rank of A is equal to R is equal to N, then N is number of unknowns, then it has a trivial solution. Next problem. X plus 3y minus 3z is equal to 0. 2x minus y plus 4z is equal to 0. X minus 11y plus 14z is equal to 0. Given this estimated matrix form, 1 3 minus 2, 2 minus 1 4, 1 minus 11 14, x y z is equal to 0. Reduce the matrix into echelon form, we get 1 3 minus 2 0 minus 7 8 0 0 7. So what is the rank of A now? 2. Number of is in echelon form, number of non-zero rows is 2, so rank of A is 2. How many variables we have? X, Y, Z. So what is the concept here? Whenever rank of A is equal to R is less than the number of unknowns, then we have infinite number of solutions by assuming n minus r arbitrary constants to n minus r variables. So what we do here is, so we have from this, if you write the equations, you get two equations. How many variables? Three variables. Two equations in three variables. We know that to solve three variables we need three equations. It's not so here. For three variables we are having only two equations now. That means we have to reduce the number of variables. What we do is, first write down the equations. X plus 3y minus 2z is equal to 0, minus 7y plus 8z is equal to 0. Let us say then n minus r arbitrary values to the assigning n minus r arbitrary values to the n minus r variables. Now n is 3, r is 2, rank is 2. So n minus r is 1. So let us say z is equal to some constant k. So we get y is equal to 8 by 7k. So if you put y and z here in this, x plus 24 by 7k minus 2z is equal to 0. Our x is independent depending on the value of k. Okay. So this is the solution. Now the x is minus 10 by 7k, y is 8 by 7k, z is equal to k. K is arbitrary constant. That means if you go on changing the value of k, the solution also changes. So how many values k can take? It can take infinite number of values. So correspond to each value of k, you get a solution. So that's why we get infinite number of solutions by assuming n minus r arbitrary constants. And that problem? X plus 3y plus 2z is equal to 0, 2x minus y plus 3z is equal to 0, 3x minus 5y plus 4z is equal to 0, x plus 17y plus 4z is equal to 0. So A is shown so high like this. Reduce the matrix A to echelon form. So this is what we get. How many equations now? The last two rows are zeros. So we have only two rows. Corresponding to these rows, we have two equations. How many variables we have? X, Y, Z. Three variables. So three variables, two equations. So rank is R is 2, N is 3. So N minus R is 1. So we have to assume one arbitrary value to one of the variables X, Y, Z. So what to do? First write down the equations here. The first equation now is x plus 3y plus 2z is equal to 0. Second one is 7y plus z is equal to 0. We put z is equal to k again. No, you can try with even y is equal to k also. There is no problem. Need not be z always. You can take y as k, z as k. That's up to you. If z is equal to k, then y is equal to minus k by 7. Okay. So put this z is equal to k and y minus k by 7 in the first equation, you will get x. So x by z is minus 11 by 7 k, y is minus k by 7 and z is k. So by giving different values to this k, we get infinite number of solutions. Okay, that's what we get. That's how we get the infinite number of solutions. Next, another problem. x plus 3y minus 2z is equal to 0, 2x minus y plus 4z is equal to 0, x minus 11z plus 14z. So this is again reduce this thing into this thing echelon form, solve the equations like this. Then these are the classical methods. Whatever we have, depending on the rank, system of equations, all that. Now gradually we will be going towards the numerical approaches and under numerical approaches, Gauss elimination method, Gauss-Jordan method, which are comfortable for us to go for a programming and this thing. So the first method is Gauss elimination method. Gauss elimination method, this is the elementary elimination method and reduce the system of equations to an equivalent upper triangular system which can be solved by back substitution. What is the underlying principle of Gauss elimination method is we reduce the given system of equation into a upper or a lower triangular matrix. In this method particularly we reduce the upper triangular matrix followed by a back substitution. Back substitution. You will see what we mean by triangle system and back substitution. Once you do a problem, understand a better way. Consider the equation 3x plus y plus 2z is equal to 3, 2x minus 3y minus z is equal to minus 3, x plus 2y plus z is equal to 4 by Gauss elimination method. The given system is like this. Okay. So consider the augmented matrix. Consider the augmented matrix. Then convert the system into upper triangular system. Upper triangular system means the elements below the principal diagonal are zeros, elements above that diagonal are non-zero. Such a thing is called upper triangular matrix. That means the non-zero elements will be in the upper triangular matrix like this. Okay. Below this diagonal elements are zeros. So once you reduce in echelon form, that means it is a upper triangular matrix almost. Now backward substitution. The last element is 8z is equal to minus 8, so z is equal to minus 1, and you substitute in the second equation we get y. If you substitute this z and y in the first equation we get the x. This is called backward substitution. In fact, what all the problems we had done earlier, we followed a similar method. It's called backward substitution method. Another problem, 3x plus y plus 2z is equal to 3, 2x minus 3y minus z, so on and so forth. So consider augmented matrix. Reduce them into upper triangular matrix, then substitute this, back substitute this, we get that is equal to minus 1, so on and so forth. You can go through the problem leisurely. Some exercise problems. Gauss-Jordan method. The only difference between Gauss-Jordan method is in Gauss elimination method we are reducing the augmented matrix into upper triangular matrix. But here we reduce this augmented matrix low. In this augmented matrix we reduce this A to diagonal matrix. We reduce this matrix A in the augmented matrix into diagonal matrix. Then obviously B also changes to B dash. Okay. Then we find a solution. Let us see. 10x plus y plus z is equal to 12. 2x plus 10y plus z is equal to 13. X plus y plus 5z is equal to 7 by using Gauss-Jordan method. The given system in matrix form is so and so. Right? Consider the augmented matrix 10, 1, 1, 12, 2, 10, 1, 13, 1, 1, 5, 7 like this. Now reduce the augmented matrix to diagonal form by applying row operations only. I said in solving system of equations you cannot use column transformations. You are not allowed to use column transformation. That's a very important rule we have. So we use the row transformation, so on and so forth. So many things are given. This is what finally we get here. But we have to reduce it to diagonal matrix like this. So when you reduce it to diagonal matrix, what happens is this A is reduced to, if it is a 1, 1, 1 diagonal matrix, D, and then your B dash is solution. That's what exactly what happens here. So 1 1 1 here, this one 1 1 1. What are the equations correspond to this matrix? The equation correspond to the first row is 1 into x plus y into 0 plus z into 0. That means 1x is equal to 1 or x is equal to 1. Similarly, correspond to the second row, y is equal to 1. The third row, z is equal to 1. So x is equal to 1, y is equal to 1, z is equal to 1. That is what we mean by Gauss-Jordan method. It's a difference between Gauss elimination and the Gauss-Jordan method. Gauss elimination method, we reduce it to upper triangular matrix. In Gauss-Jordan method, what we do is we reduce it to diagonal element matrix, preferably identity matrix. Solve the equations. So A is given like this. Apply row transformations. You comfortably go through these things. So like this is what happens. So by the time it reduces to 1 1 1, it will 1 1 1. So x1 is equal to x2 is equal to x3 is equal to 1. This is how we get the solution. Solve the system of equations using Gauss-Jordan method. Two problems are given to you. So this is LU decomposition method, or this is also known as method of factorization. The method of factorization. So if AX is equal to B, that is a system of equations given to us. Then LU decomposition method, the matrix A is expressed as the product of lower triangular matrix and upper triangular matrix. Lower triangular matrix and upper triangular matrix. Like this, where L is L11 0 0, L12 L22 0, L31 L32 L33, and U11 U12 3. Like this is upper triangular matrix and this is lower triangular matrix. Assume that L11 is equal to 0. That means phi is equal to 1 2 3. That means diagonal elements are 1. That means while decomposing this matrix A into L and U, see that this L11, L22, L33 are 1s. Now AX is equal to B. Because A is equal to LU now, put this LU here. This equation becomes LUX is equal to B. Because A is equal to LU. Put them here, LUX is equal to B. And if you call this UX as B, as some Y now, UX is equal to Y, then this becomes LY is equal to B. LY is equal to B, where AUX is equal to Y. So this is a basic idea. From this we get the decomposition. Let us see what happens. The given equation to form the given system of equations. Let us say, as I said, the principal diagonals will take ones. So 1 1 0 1 0 0, L21 1 0, L31 L32. This is also 0 actually. It's not misspelled as 0. So U11 U12 U13 0 U22 U23 0 0 U33, and this total thing is matrix A. Now expanding, what happens? What is the first row? 1 into U1 multiply with the first column 1 into U1 0 0 0 0. So you get the left hand side will multiply the first element is U11 1 into U11. The right hand side is 1. So your U11 is known to you now. And multiply the first row with the second column U12 plus 0 plus 0. So what is U12? 1 into U12 is equal to corresponding element is 5. So U12 is 5. So it appears to be a very big process, but very easily you can do the problem. Then if you multiply the first row with third column here, 1 into U13, 0 into 0, 0 into 0. So what is U13? So U11, U12, U13, these three things are known. Okay, first row. So coming to the second row, multiply the second row with first column, L21 U11 plus 1 into 0. So what happens to L21? U11 is 1. So L211 into 1 is equal to 2. So L21 is 2. So multiply the second row with second column, L21 U12 plus 1 into U22 plus 0. L21 U12 plus U22 is equal to, what is the element here? 1. Do you know any of the elements here? L21 is known to you. You put it here L21. So U12 plus U22 is equal to 1, but U12 is 5. So U22 is known to you minus 9. Like this, we calculate this L11, Lij and Uij here. Then Ax is equal to B becomes Lux is equal to B, and Ux is equal to, let us say, Y, then Ly is equal to B. Ly is equal to B means this is L, Y1, Y2, Y3 is equal to B, 14, 13, 17. So Y1, Y2, Y3 are easily calculated. Once Y1, Y2, Y3 are calculated, then Ux is equal to Y. So upper triangular matrix into X is equal to Y. Now it is echelon form, and clearly minus 5 by 9 Z is equal to minus 5 by 3. Or substitute, then backward substitution, we get X is equal to Y is equal to Z. This is called LU decomposition method. We decompose this matrix. See, this is a bit lengthy problem, and gate examination you cannot expect such a problem in just a short multiple choice question. But the procedure, you may have some questions on the procedure that you have to be ready, and you have to answer such questions. So like this, another questions on LU decomposition. Like this, we consider this unit diagonal elements once along diagonal elements of L, and then using those ones we get this U11, U12, U22, so on and so forth. So this is LU decomposition method. Exercise problems on LU decomposition method. And then before going to eigenvalues and eigenvectors, because because still we have 20 minutes time, it is, I think, maybe difficult for us to find do the problems and properties and eigenvalues and eigenvectors. Let us see. Start with some of the basic questions. Some questions and till now short answer questions. Some questions, I mean, like MCQs on matrices. So just let us go through these questions on matrix series. A square matrix is said to be lower triangular matrix if you understand lower triangular matrix. I say we have seen LU decomposition L. What is the structure of L? Yes, a square matrix is said to be lower triangular if Aij is equal to 0, Jij greater than J, Aij is equal to 0 for I is equal to J, Aij is equal to for I less than J. So this we have to think which one is the correct one. Key is given to you, no problem. Don't worry, but try it on your own. Try it on your own. So lower triangular is like this. This is lower triangular matrix, LU. This is second column, first row. This is third column, first row. So I is 1, J is 2, J is 3. That means clearly I is less than J. Here also I is 2. Here it is. I is 2. J is 3. 0. Okay. So what do you understand here from this? Whenever I less than J, Aij's are zeros. Then that is called a lower triangular matrix. AB whole inverse is equal to, you know what it is. Matrix A is said to be skew symmetric matrix if A transpose is equal to, I already discussed this issue with you. A transpose is equal to minus A. LU decomposition method fails if LII UII is equal to, yes, these are the things, most important point that you have to understand. When Thus, the LU decomposition method fail. When LAI UI equals 0, what happens? In LU decomposition methods, we are dividing with LII UII. When they are zeros, decomposition method fails. The system of equation AX is equal to B has infinite number of solutions. I told you, don't throw away the theory questions. Okay, because you have a less regard towards theoretical questions. You always feel like problems. But what happens is in GATE examinations, straight away they are asking some theory questions also. Yeah, this one, the theory questions. This one is a theory question. This one is a theory question. This one is a theory questions. The system of equation AX is equal to B has infinite number of solutions. When infinite number of solution is also a solution. So it's a consistent. The system is consistent. That means rank of A is equal to rank of augmented matrix. That is for sure because we have infinite number of solutions. But the rank must be less than number of unknowns. Less than number of unknowns. If this happens, then it has a unique solution. Rank cannot be greater than n. So this is also wrong. So it is less than n, then we have infinite number of solutions. Every minor of order A of order R of matrix A is non-zero. The rank of A is the definition of rank of matrix. The solutions of system of equations. We have to apply general inversion method, we apply Cramer's rule, we apply Gauss elimination method or Jordan method, whatever method you apply, you have to solve the equation. Or else, if you can do smartly, substitute the points one by one quickly in all these equations. That is another way, indirect way of doing it. I don't advise it. But if the time is running quickly, then instead of applying all the row transformations and column transformations, you people are asking me tricks. No, this is one trick you can do. Substitute this 1 0 0 in all the equations. If you put 1 0 0, it is satisfied. If you put 1 0 0 here, satisfied. If you put 1 0 0 0 here, no. What happens? 5 into 1 0 0, but it's 3. Not satisfied. So A is not correct. If you put it here, x y 0 0 0 1, good. 0 0 1, good. 0 0 3, good. Satisfies. This will not satisfy, and this will not satisfy. So this is the solution. That way you can. That's a trick you can apply. You're asking me tricks, no? Instead of applying the Gauss Jordan and Gauss elimination method, if you apply substitute the points in all these equations, you can check which of the alternatives is a correct alternative. Suppose A and B are 5 by 5 matrices. What is A plus B whole square? A minus B whole square. This is A square plus B square plus. Then there is a small this thing 2AB plus 2BA. Just be very careful with this. It will not be like A square plus B square plus 2AB or 2BA. Okay, just be very careful with this. Just try it. It is very logical question. Try it. Which are the following or linear functions? If y is equal to f of x, where x is a 2 vector and y is a 2 vector. So this you try it. Linear functions. Which are the following functions are linear functions? y1 is 3x3 minus x2, y2 is x2 plus 3x3 minus x1, y1 is equal to x2, y2 is equal to both 1 and 2. The set of linear equations can be represented. So this is also which of these equations are linear and all that. So you can do this. All these basics of vector spaces. Solving a set of 100 linear equations in 100 variables. Easily done by hand. You do it a 100 by 100 matrix system. Is a dangerous task that should be done by certified professionals. Silly option can be done is in less than a second on a small PC. Is a problem that rarely comes up in practical problems. Requires about a minute or professional work. None of them is correct. Okay, the 5 vector x lies 5 vector x is a solution of the linear equation Ax is equal to B where A is a 5 by 5 non-singular matrix, Y is a solution of linear system, Y is AY is equal to B. What can you say about X and Y? Okay. You have to get the relation between these two. A is a non-singular matrix, so X is equal to A inverse B. And from this Y is equal to A inverse 2 into A inverse B. So from this you can derive a solution. So you can try the problems in this way. And so we are in the middle of the linear algebra. We are yet to start with eigenvalues and eigenvectors. So we'll discuss the definition and we'll stop. We have almost 10 minutes more. 10 minutes more. So we'll discuss eigenvalues, eigenvector, definitions of eigenvalues, eigenvectors, and we'll stop there. So what is an eigenvalue and what is an eigenvector? That A, B, and N by N matrix. Mind you, when I say eigenvalues and eigenvectors of a matrix, don't ask me A is a square matrix or a rectangular matrix. A must be a square matrix. A must be a square matrix. That N by N matrix, there exists non-zero vector x such that Ax is equal to lambda x. Mind you, remember, when I say x is an eigenvector, then it cannot be a zero vector. It must be a non-zero vector. The definition itself, we are using this non-zero vector x such that Ax is equal to lambda x. Then lambda is called eigenvalue, and the corresponding vector is called eigenvectors. See, if x is a zero vector, if you put it x is equal to 0 here, anyhow it satisfies. So it is no fun in having a zero vector here. What is non-zero vector? You have to find that non-zero vector which satisfies Ax is equal to lambda x. Then lambda is called the eigenvalue and x is called the eigenvector of A. So for simple case, A is equal to, now this is a wonderful verification. Sometimes a matrix is given to you, vector is given, eigenvector is given to you, and you will be asked to find the corresponding eigenvalue. What is that? You know eigenvalue, you can find eigenvector. Now, matrix A is given to you and the corresponding eigenvector is given to you, then you are asked to find the eigenvalue. What is the property Ax is equal to lambda x? You use this property. So A is given, x is given, multiply them, Ax is equal to into Ax, A into x. That's what is called 6. What you get is 6 minus 3. Can you write this 6 minus 3 in terms of this x? 2 minus 1. To take 3 common, this will be 2 minus 1. So this is constant into x. So Ax is equal to lambda x. What is your value of lambda now? 3. So our Ax is equal to 3x, lambda becomes 3. Similarly, if A is 4215, x is 1 is an eigenvector, what is the corresponding eigenvalue? This is a very short answer question. We can expect such questions in the gate. So multiply A into x, we get 6. This you can write as 6x because 1 is eigenvector. So what is your eigenvalue? 6. 4125 and x is 1 2 is an eigenvalue. Multiply Ax, you get 811. Can you identify it as a scalar multiple of this x12? Because this is 811. You cannot write it as a lambda times 1 2. You cannot find a real number lambda which gives lambda into 1 2 is equal to 8 into 11. So 1 2 is not an eigenvector. 1 2 is not an eigenvector. If you can write with some real number, need not be integer even, then you can call x as a eigenvector. But such relation is not valid here. So 1 2, the vector given vector, it cannot be an eigenvector of A. Procedure to find eigenvalues and eigenvectors. Okay. Let A be n by a matrix and lambda be the eigenvalue of A and x by the corresponding eigenvectors. Then we have Ax is equal to lambda x and x not equal to 0. Or else you take this lambda x or say Ax minus lambda Ix is equal to 0 or A minus lambda I into x is equal to 0. So if you call this is a quotient matrix now. Some quotient matrix Bx is equal to 0. This is homogeneous system of equations for which x is always a solution. X is equal to 0 is always a solution, but we don't want x to be 0 because we want the non-zero solutions. For non-zero solution in homogeneous equations, I told you we have only two options. Either we have a trivial solution or infinite number of solutions. There is no issue like there is no solution because trivial solution is always there and infinite number of solutions we have. So trivial solution we don't want. So the only option before us is infinite number of solution, which is a homogeneous system of equation. The system possesses a non-zero solution. If the quotient matrix is singular, then we have infinite number of solutions. So infinite number of solutions, non-zero solutions exist whenever A minus lambda I is equal to 0, and this is called characteristic equation. So the eigenvalues are nothing but the roots of the characteristic equation. They are also known as characteristic values. And another important name for the eigenvalues is latent roots. So eigenvalues are characteristic values or latent roots. There are three different names that we use for eigenvalues. So eigenvalue of a matrix may be 0. Eigenvectors of a matrix must be non-zero. Eigenvectors corresponding to eigenvalues are not unique. Say for example, lambda is equal to 1 is an eigenvalue and the corresponding eigenvector is x. Okay, so we have done this in these problems. So 1 1 is an eigenvector, 6 6 is also an eigenvector. Scalar multiple of eigenvector is also an eigenvector. In that sense, eigenvector need not be unique. So these are three important points. Eigenvalue of a matrix may be 0, but eigenvectors cannot be 0. They are non-zero. Eigenvectors correspond to eigenvalues are not unique. Find the characteristic roots of matrix 1 1 1 1 5 1 3 1 1. So first construct the matrix A minus lambda I matrix A minus lambda I. Take the determinant equal to 0. Solving determinant we get lambda cube minus m lambda square plus 36 is equal to 0. If we expand this determinant A minus lambda I, this is what we get. So the roots of this you have to find. So minus 2 3 6. Question now is whenever you deal with such problems, when I do such problems, I always verify it whether the roots you are finding are correct or not. Maybe if there is a mistake in your characteristic polynomial, your eigenvalues will go wrong. So immediate verification is sum of the eigenvalues is equal to trace of the matrix. This is a very important property of eigenvalues. Sum of the eigenvalues is equal to trace of the matrix. What is sum of the eigenvalues here? Minus 2 plus 3 plus 6. So that comes 6 plus 3 9 minus 2 7. Then what is the matrix A? What is the trace of the matrix? Trace means sum of the diagonal elements 1 plus 5 plus 1 7. Sum of the eigenvalues minus 2 plus 3 plus 6 7. So these eigenvalues you have obtained are correct. That is an immediate verification. These are called characteristic roots or characteristic values or latent roots or eigenvalues. Sometimes eigenroots also. There are different names we have. So this is how we get eigenvalues. Find the eigenvalues and eigenvectors. Consider determinant of A minus lambda is equal to 0. Expand the determinant equal to 0. We get characteristic polynomial or characteristic equation. Find the roots of that minus 1, 1, 2. Again verify whether the eigenvalues are not correct or not. Minus 1 plus 2. Sum of the eigenvalues is 2. What about the matrix? Add the principal diagonal elements. 3 plus 3 minus 4. 3 minus 4 plus 3. 6 minus 4. 2. Sum of the eigenvalues is 2. So the eigenvalues are correct. So how to find the eigenvectors now? So corresponding to lambda is equal to 1. What are the eigenvalues? 1 minus 1, 2. Corresponding to lambda is equal to 1. If you put lambda is equal to 1 here, this equation a minus lambda into x becomes this equations. So this is again a homogeneous system of equation. Reduce the matrix to echelon form. So this will be like this. If you solve this equation, x2 is 0. And the first equation becomes 2x1 minus 2x2 plus 2x3 is equal to 0. Because x2 is equal to 0, x minus x plus or x1 plus x3 is equal to 0. So if you put x3 is equal to k, x1 becomes minus k. So eigenvector x is x1, x2, x3, x1 is minus k, x2 is 0, x3 is k, or k times minus 1, 0, 1, or hence minus 1, 0, 1 is an eigenvector A corresponding to lambda is equal to 1. Similarly for lambda is equal to minus 1, if you put a minus lambda, if you put lambda equal to minus 1 in a minus lambda A, this is a system of equations. Convert this to reduce to echelon form, this is what we get. Echelon form. And this also can be reduced to 0, 1 into R2. If you multiply this with 3 and subtract from the other one, this will be 0. So from this what happens? 1 into x2 is equal to 0. So x2 must be 0. Okay. Either way, x3 or x2, some of these two things must be 0. So we get another eigenvector. Coming to lambda is equal to 2. Put this lambda is equal to 2 in a minus lambda is equal to 0. So this is the matrix equation we have. Then reduce it to echelon form like this. So y minus z is equal to 0 or y is equal to z. Y is equal to z. If you say y is equal to z is equal to k, what happens? 1 minus 2y plus 2z is equal to this thing. So we get x1 is 0, x2, x3 is equal to k. The eigenvector is 0, 1, 0. Okay. Properties are, so I stop here before going to the properties. Okay, so many problems and properties we have to deal with here, eigenvector properties and problems. So we'll sort out these things, discuss these things in the next class. So and we'll discuss the eigenvalues, properties of eigenvalues, eigenvectors, and then we have to discuss gate problems, previous question papers in matrix linear algebra in the previous gate papers. Tomorrow we will discuss those two issues. We will finish off eigenvalues, eigenvectors, and previous gate question papers. What are the questions that are given in linear algebra in previous gate question papers? So with this, so with this class comes to an end. Wish you all the best, and if you have any doubts, you can always give me a mail. You know that you have that Excel sheet and all that. I will respond to your questions. Okay, thank you. Bye.